Good afternoon to everyone. We continue our course of semiconductor and electronics, and on the previous lecture we have finished with the consideration of Schottky junction. Actually, we have formulated the Drift-diffusive equations, which are the basis for computation of current voltage characteristics of any semiconductor device. And now, today, we will apply them to one of the most important devices in electronics, which is the Schottky die. The outline of the lecture is the following. First, we will attempt to find the current voltage characteristic of a Schottky junction in the so-called Drift-diffusive approximation. The second part of the lecture will be devoted to the consideration of the same problem within the ballistic approach. The difference between these two is that when we consider Drift-diffusive the Drift-diffusive transport, then we think that electrons are moving. Probably another. Then we consider the electrons to be moving with very frequent collisions, for example, with lattice defects or phonons and so on. The first approach, which is Drift-diffusion approach, is valid when the free path length of electrons is much smaller than the length of the device. And in each section, we can apply the equations of Drift-diffusive conductivity. In the other limit, when length of free path is much larger than device length, we can consider that the parts of the device work as reservoirs which supply electrons into the channel, and then they pass through obstacles ballistically without any collisions. According to the laws of classical mechanics, this will be our case, or according to the laws of quantum mechanics, which is quite a simple generalization. In the last part of the lecture, we will consider the so-called combined approach to the transport, when which is valid in intermediate situations, when length of free path is still smaller than the length of the device, but it is important and makes a considerable fraction of the total length. Please ask any questions if you have some probably misunderstandings. And the conceptual importance of our lecture is not that we consider a Schottky junction. Schottky junction is quite an old device, and it is scarcely seen in modern electronics. Despite we every time have metal semiconductor contact, this topic is quite classical. But what is conceptually important, that we will illustrate two approaches to the calculation of transport, and these two approaches will be applicable in many different situations, in many other devices, like transistors, PN diodes, probably solar cells. You can also describe other devices with these two approaches, depending on the ratio of free path and device length. So let's continue, let's move on. And here I remind you the energy band diagram of the metal semiconductor structure. We consider a contact of metal and n-doped semiconductor. The fact that this semiconductor is n-doped is manifested in the following observation. The distance between Fermi level and conduction band bottom, this difference between conduction band and Fermi level, is much less than the band gap. It means that the Fermi level is quite close to the conduction band bottom. We have already considered and we have already proved that when we place this semiconductor in contact with metal, the diffusion sets in and electrons start diffusing from n-doped semiconductor into metal. Here we have some depletion layer, And in this depletion layer, we have almost no electrons and only donors. Well, not strictly speaking, not only donors, but mainly donors contribute to the charge. And the charge density here is just elementary charge by the density of ionized donors. The distribution of electric potential here is almost parabolic. So here is the top of the parabola and here it continues. This depletion region has negative charge, and what is very important, we have some energy barrier formed formed for electrons. As the electrons leave this region, the remaining positive charge makes a barrier to stop the electron diffusion from undoped semiconductor into metal. And this barrier is very important for the transport. For example, when we want to consider some non-equilibrium situations, if we apply the bias voltage so that the band diagram is bent downward, the barrier for electrons goes higher. And here we have he will have no current. And if we apply the bias such that the band diagram is bent upward, this situation will correspond to large current. This is just our intuition. We will prove these statements by rigorous calculations. And it appears that the current voltage characteristic of a Schottky junction is very asymmetric in one direction. When we apply negative voltage and hence raise the potential energy for electron in the right side, the current will be large. And when we apply positive potential to the semiconductor side, the current will be low. The resulting current voltage characteristic looks like that. So on the forward current region we have large current density, and in the backward current region we have very small current density. What will be important for the further considerations is the shape of electric potential in the semiconductor. This can be found, as we did before, just by solving the Poisson's equation in the so-called full depletion approximation. The full depletion approximation means that we consider some area inside of semiconductor of yet unknown width W, in which we can neglect the charge of electrons, and we can approximately set the density of electrons to be 0. In this case, the Poisson's equation contains only the donor density in the right-hand side, and it is easily integrated with two unknown integration constants. One is the constant offset, and the other one is the unknown linearity coefficient. These two parameters, in addition to the unknown depletion width, can be found from the following statements. We can just arbitrarily set the potential here to be fully flattened out. This region is roughly neutral outside of the depletion region. So we can assume that the potential here is 0. The potential here is also smooth, which means phi prime at W is also equal to 0, and we also know that at the origin of the junction, the height of electric potential is equal to the built-in voltage. The built-in voltage is nothing but the difference between work functions of metal and semiconductor. It is just a tabular value for any contact of a known metal and a known semiconductor. So doing this way, we can find the unknown constants V at the surface and electric potential and constant value F. Actually, already from this first boundary condition, we obtain that the constant Vs is nothing but the built-in voltage. And the only thing we need to find is the remaining field F. This is the only unknown constant. It can be found from the condition, for example, of smoothness. Phi prime at the end of depletion width is 0. From this consideration, we can find that F equals 4 pi E divided by the electric constant of semiconductor multiplied by the donor density and multiplied by the width of the depletion region. The final thing we need to find is the width itself. It is found from the third boundary condition, and this important expression is written here in the bottom of my board. It is written in two kinds of units, in Gaussian units and in the C units, where we have restored the vacuum permittivity epsilon 0. Well, roughly at donor density of 10 to 18th units per centimeter cubed, this width is order of 1 micron. But you can calculate it by yourself for various kinds of semiconductor. For reference, the typical values of built-in voltage are roughly 0.4 EV. So you can estimate this number quite easily. It is hundreds of nanometers or several microns, depending on how strongly you dope the semiconductor. So, but one more important thing is, can we attempt to guess the shape of electric potential when we consider this junction in a non-equilibrium situation? Of course, in non-equilibrium situations, to find the electric potential versus coordinate, you need to solve the full set of drift-diffusion equations. But still, you can make a reasonable guess. For example, if you bias the junction, let's close it all and repeat it once more. For example, when you bias the junction by the amount of extra voltage EV, what would be the shape of electric potential? The shape of electric potential can be found by very similar considerations. So you can just change the boundary condition for electric potential at one of the ends. So you can still set the zero level to be here and just change the boundary condition on this side and set the potential at phi equal to 0 would be equal to built-in potential minus applied potential. And this would be the only change that you need to introduce into these formulas. In this case, the solution for the Poisson's equation would be V built-in minus V applied plus electric field by the coordinate minus 2 pi E epsilon semiconductor donor density x squared. And the expression for the constant F would be indifferent. when we bias the junction, and the expression for the depletion width would change. The built-in voltage should be replaced by the built-in voltage minus applied voltage. I write everywhere the moduli of applied voltages because the signs should be determined just by your intuition. Like in this situation, the barrier has emerged, therefore the built-in voltage is negative and the potential energy is positive, and the applied voltage to this side is also negative because we have raised the potential energy of electrons, but both are negative and the absolute value of the barrier height has reduced. Please ask any questions, because afterwards we will need to pass to considerations of electron transport. Don't be shy. Okay, to find the current voltage characteristic of the junction, we will not solve the full system of the Drift-diffusion equation because it is actually not solvable analytically, even in this simplest case of the junction. Instead of that, we will assume that the electric potential is known, and it is given by this formula with the constants that we have found from the boundary condition. So we assume that the profile of electric potential phi is known, and we will find the distribution of electric current, including the drift and diffusive components, under assumption of known potential structure. Actually, it is not so simple as it may appear, because the background electron density is highly non-uniform in this junction, and you cannot apply simple Ohm's law. So what we will need to solve? We will need to find the current which is contributed both by drift component. The drift component is proportional to the gradient of electric potential, and diffusive component, which is proportional to the gradient of local Fermi energy. Actually, you can rewrite this diffusion component in terms of gradient of the density and diffusion constant. The both of these quantities can be combined into the so-called gradient of the quasi-Fermi level. Quasi-Fermi level is the difference between local Fermi energy and electric potential E phi. So these quantities are shown here by various colors. This picture is very important for further considerations. So we have biased a junction slightly so that the barrier has reduced compared to the equilibrium situation. This is the so-called forward bias, when we expect exponentially increased current. The difference between Fermi levels in the metals and deep in the bulk of the semiconductor is the measure of non-equilibrium in this situation, and it equals exactly EV, where V is the voltage applied to the battery, applied from the battery, from the external voltage source. Particularly in this situation, the metal contact is considered as grounded, and this contact is considered as electrically biased with negative bias V. When the electron travels from one end of the structure to another, its quasi-Fermi level gradually evolves from one equilibrium deep in the contact to another equilibrium deep in the contact. So the drift diffusion model assumes that the electrons are equilibrated injected from semiconductors are equilibrated with metal immediately at this boundary. So the Fermi level drops from the value of E modulus V at the right side to 0 at the metal side. But still the evolution of this Fermi level with coordinate is not known. It is a sought for quantity. The current density is also a sought for quantity. So it appears that the situation is quite tricky because we don't know the current and we don't know the quasi-Fermi level. Can anybody suggest a method to find the current if we don't know the distribution of Fermi level and distribution of density inside of the structure? Don't be shy. Actually, one equation and two unknowns. One is just a number we need to find, and the other one is a function. The boundary conditions are also known. We have the Fermi level at 0 to be 0 and Fermi level at plus infinity to be E modulus of applied voltage. So at infinity it is higher than at 0 by the amount of voltage supplied by the battery. It's a good hint because we have a first order differential equation, but we have two integration constants. Can we resolve it simply? Okay, and actually there is one more question to you. Can the current density in this situation vary in space? Can it depend on coordinate itself? Is the current density a function of a coordinate or it is just a constant?
It should be a constant.
Excuse me?
Can you hear me?
Well, could you repeat once more, please? I don't hear.
Can you hear me now?
Okay, the current density is a constant here. It is not a function of a coordinate because it is, according to the continuity equation, it should be constant everywhere. Otherwise, the charge will be accumulated along the structure. You remember that if the continuity equation, which tells us that if we have non-uniform current, then the charge will be accumulated. And as soon as we assume the steady state character of this equation, then the current should be constant. Actually, this constant value of the current allows us to integrate both parts of this equation to get rid of one of the constants. But before doing this, we will need to express the density in terms of local Fermi energy and local position of the conduction band. The density at each point is the effective density in the conduction band. Effective density of states in the conduction band is just a tabular value for each semiconductor multiplied by exponent by the local difference of Fermi level and the conduction band bottom divided by KT. So this is a function of coordinate. This is also a function of coordinate. But the position of the conduction band is nothing but the electric potential with opposite sign, because position of the conduction band is the landscape of the potential energy. So as soon as we assume phi as a known function, then we also know how energy of the conduction band evolves. So this is a known thing. Now what we do next? We substitute the expression for the density of electrons in the expression for the current and split the variables. All the stuff that contains quasi-Fermi level is retained in the right-hand side, and all the stuff that is associated with conduction band bottom depending on the coordinate is moved to the left side. What we obtain as a result, J multiplied by exponent of conduction band bottom divided by KT multiplied by dx is equal mobility multiplied by effective density of states in the conduction band multiplied by exponent of quasi-Fermi level divided by KT and derivative of this quasi-Fermi level. And now both parts of this equation can be integrated from one contact at 0 to another contact at infinity. If we operate in the full depletion approximation, then we don't have to integrate to infinity, we integrate just till the depletion width, which is the only part of interest for our junction. Then what we obtain is J multiplied by the integral from 0 to depletion width over coordinate multiplied by exponent of conduction band bottom divided by KT equals mobility, effective density of state, KT multiplied by the integral of exponent from 0 to EV. What is it? It is exponent of EV divided by KT minus 1. So we have integrated the left part of this expression by coordinate from one contact to another, and at the same time the quasi-Fermi level was integrated from 0 to its value governed by the voltage source EV. And this is all. This is the final expression for the current. We can now express the current from this algebraic equation. Let me now close the derivation. We can repeat it. It is very simple. And the final result is the current density is proportional to mobility, effective density of states in the conduction band, thermal energy. These two can be merged into the diffusivity D for electrons Dn, some exponent of applied voltage, and in the denominator we have some quantity with the dimension of length. It can be just called some effective length of the junction, no matter. It depends on voltage very smoothly, softly, and I promise you that it contains no extra exponents that could beat the first exponent in the numerator. So you can easily check it by writing that conduction band bottom is the inverted potential, and potential can be taken from full depletion approximation. Full depletion. I have tried to evaluate the current voltage characteristic given by this formula at home and for some realistic density in the semiconductor, like the density of donors equal to 10 to 18th and other parameters corresponding to silicon. So the typical current densities are roughly tens amps per centimeter squared. The current is exactly zero at zero bias, is governed by the equilibrium situations, equilibrium considerations, and it is exponentially small on the left side. Actually, if you combine these two functions and analyze them in much detail, you will see that this thing is proportional to the electron density at infinity, multiplied by the quantity exponent of built-in voltage divided by kT. So it can be interpreted as a fraction of charge carriers at the right end that can overcome the energy barrier. And this analysis, I think, is very important. You can do it at home knowing the expression for the conduction band bottom versus the coordinate. Please ask any questions. Don't be shy. So, if no questions, I would like to repeat the general formalism that we have used. How to derive the current voltage characteristics of any junction using the drift-diffusive approximation. This is not a strict procedure, but it works fine in many cases. First, you need to specify the carrier density in terms of conduction band bottom and quasi-Fermi level as conduction effective density of state by exponent of quasi-Fermi level minus EC divided by KT. Then split the equation into in the way that the left-hand side is dependent only on coordinate, x-dependent, and probably here you will have conduction band bottom depending on x, and on the right-hand side you will have the other part depending on quasi-Fermi level, fan-dependent. And then just integrate over coordinate and quasi-Fermi level. Integrate over the coordinate x from source to drain, and quasi-Fermi level would be in the range from 0 to applied voltage. And then by integration of such kind of equation you can get the final current voltage characteristics. I will repeat that it is applicable not only to Schottky junctions but to more complicated structures as well. The other approach I would like to highlight is the approach based on ballistic theory. Ballistic theory assumes that the charge carriers are moving without any collisions. And the principle of calculation is quite different here, and the results would be different as well. When we consider ballistic transport, the concept of quasi-Fermi level becomes not much important, because the equilibrium between charge carriers is only somewhere deep in the contents, where the carriers can collide with each other quite frequently, and this can lead to thermalization. In the junction itself, which is quite short, the equilibrium is absent. So we, frankly speaking, cannot describe their distribution by Fermi function. So the concept of Fermi level is meaningful only here, and then we can continue it arbitrarily in the bulk, like we can consider it as a constant. It will be not so important. And the problem of finding the current voltage characteristic in this case is formulated as follows. We have two reservoirs of electron. Reservoir in metal, reservoir number 1, and reservoir deep in the semiconductor, reservoir number 2. These reservoirs are characterized by equilibrium distribution functions, like F distribution function in metal depending on energy, and distribution function in semiconductor. It is also depending on energy. The only thing we know about these distribution functions is that the Fermi levels are shifted by the amount of EV. So the Fermi level in metal and Fermi level deep in semiconductor differ by each other by the value of applied voltage. Fs minus Fm equals E modulus V. So these functions are all known. The Fermi levels between them are known as well. And these reservoirs supply electrons that move ballistically and can either propagate over the energy barrier or be reflected from this energy barrier if their energy is not enough, and if it is not sufficient to overcome the barrier. So to find the current, we need to calculate the flux between semiconductor flowing from semiconductor to metal supplied by reservoir number 2 and subtract the opposite flux from metal to semiconductor, which is supplied by reservoir number 1. The computational rules for this current are just to calculate the average number of particles in unit time that can overcome the energy barrier. I would like to remind a problem from molecular physics from probably your university course that is very reminiscent to the problem of finding the ballistic conductivity in the Schottky junction. Probably most of you have solved it. The problem was formulated in a similar way. One could consider the bulb with two portions, with two sections, having different densities of gas molecules, N1 at temperature T1 and N2 at temperature T2. And there was a small orifice inside or between these sections. The area of this orifice was much smaller than the free path length squared. And the problem was to find the flux between these two sections. Probably you can remember the answer in terms of average molecule density and thermal velocity. Does anybody remember these beautiful results from molecule theory? Yes, I see in the chart NV divided by 4. Yes, it is a good answer. It could be derived from Maxwellian distribution. In this case, the flux from left to right was equal N1 divided by 4 multiplied by thermal velocity at temperature T1, and the opposite flux was N2 divided by 4 thermal velocity at temperature T2. Actually, if you know how to find this solution from molecular physics course, then you can solve the problem of current voltage characteristics in the Schottky junction, because it is very, very identical, at least from the semiconductor side, because in the semiconductor side the density of electrons is small and it is well described by Maxwellian statistics. For the metal side it is slightly more complicated because you have Fermi statistics here, but we will be able to sneak out from this situation. So probably if you know this answer from molecular physics, when there was no energy barrier inside of this orifice, could you imagine how the result would be different in the case of the energy barrier from semiconductor side? So assume that the density of electrons at infinity is known and it is equal N infinity. We could speculate that the current from metal to semiconductor would be equal to N infinity divided by 4 multiplied by thermal velocity in semiconductor. Probably you can imagine a simple way to introduce a correction for the finite height of the energy barrier. Any idea, please? Just your intuition. In the case of gas, we had no energy barrier and the flux was equal to density multiplied by thermal velocity divided by 4. Here we have an extra obstacle that we need to overcome. The height of the obstacle is known. There is some suggestion in the chart that we will need to introduce a theta function of the velocity minus velocity that we need to overcome the barrier. It is a good suggestion for the intermediate calculations, when further the velocities have to be integrated over the Boltzmann distribution. And in the final result, we will get that only a small fraction of molecules, or actually of electrons in our Schottky barrier, would be able to overcome this energy barrier. So this fraction would be just the Boltzmann exponent of minus built-in voltage minus applied voltage divided by QT. So now let us try to, I have announced the correct answer. Actually, this answer is correct, at least for the current from metal side to the semiconductor side. And now let us try to prove it more rigorously. The proof would be important for the further calculations because it is a general formalism to calculate the transport inside of ballistic junctions. Let us find the flux of electrons flowing from metal to semiconductor side. The flux is nothing but the average velocity. You know already how to find the averages. You multiply the charge by degeneracy factor, which is 2 for electrons. You need to integrate over momenta the quantity of interest, the x component of velocity, with the distribution function at the semiconductor side that depends on the energy. The integration here occurs only over the charge carriers that are moving to the left. So not over all the phase space, but over the half of the phase space, or over the particles that have negative momentum. The straightforward way to do these kind of integrals in the previous sorts of lectures was to pass to the polar coordinates. But in ballistic calculations, the other approach is preferable. You need to split these integration variables into energy variable and transverse momentum. Transverse momentum is the momentum directed in the plane of the Schottky junction. So if this coordinate is x, then transverse momentum is the momentum lying in the plane being transverse to x, so in the yz plane, which is the square root of px squared, py squared plus pz squared. The reasoning for that, the reasoning for these variables to be convenient is that these quantities are conserved when particle is moving in the complex landscape, because its direction over x coordinate is affected by the electric potential, and x component of momentum is changing. We cannot track it. It is complicated to track it everywhere in space. So we integrate over the variables that are conserved upon transport. These variables are conserved. How it is most convenient to pass to the conserved variables? First of all, you recall that summation over momenta is identical to the integration over px, py, pz divided by 2ph cubed in three-dimensional situations, and you also need to multiply it by velocity. But velocity, according to the Hamilton equations of motion, is nothing but derivative of energy with respect to the momentum px. Delta energy, delta px. Then the variable that we don't like, the px variable, cancels out automatically, and we are remained with the integration over the energy and over the transverse momenta dpy dpz. When working with these transverse momenta, it is convenient to pass to the polar coordinates, and the answer will look like it is the integral over energies divided by 2ph cubed, and integral over transverse momenta. The transverse momentum has two components, so here we write the area of the ring. 2 pi momentum transverse, delta momentum transverse, and something that we will need to integrate further. The limits of integration would be determined right soon, because they are governed by the energy and momentum conservation laws. So the current flowing from metal to semiconductor is the elementary charge multiplied by the spin degeneracy factor, integral over energies divided by 2ph cubed. The distribution function depends only on the energies, so it can be factored out, and we need to integrate over the transverse momenta to 2 pi momentum delta momentum. The transverse momentum can range from 0 to some value at given total energy. This value at given total energy would be actually determined by which particles can pass through the barrier. The energy of a particle, if we consider it if we consider the particle that can pass above the barrier, should from one hand be greater than the barrier height. Let us denote this barrier height as UB. From the other hand, we can write the energy which has kinetic component and potential component as barrier height plus px squared divided by 2m plus p transverse squared divided by 2m. If the particle has a critical energy which is just slightly above the barrier, it means that it stops its velocity to 0 at this point. This critical particle has the momentum px tending to 0, so we can cancel this term. Then its transverse momentum, p transverse maximum, would be equal to square root of 2 masses multiplied by the energy reckoned from the barrier height. This is the expression for the maximum transverse momentum. It is determined by the condition that a particle with critical momentum stops exactly at the maximum barrier height. So we integrate over momentum from 0 to square root of 2m energy minus barrier height. What about energy integration? The energy integration also occurs from barrier height to plus infinity. Only high energy particles can pass through the barrier. This is a trivial part. We integrate it very simply. It is a power law function. So we can write yet an exact result, qg 2ph cubed, integral from barrier height to plus infinity, Fermi function in the semiconductor depending on energy, and multiplied by 2 pi m energy reckoned from the barrier height. The only thing that is remained here is to integrate this Boltzmann exponent with the a linear function energy minus barrier height. It is quite simple stuff. The distribution function in the semiconductor is just exponent of energy minus Fermi level divided by kT, where we can erase energy minus barrier height is the new integration variable psi, and there is a trivial integral that we need to evaluate in the middle, is the integral from 0 to infinity psi, the psi exponent minus psi divided by kT, which is nothing but kT squared. So the final result would be qg divided by 2ph cubed 2 pi m kT squared multiplied by exponent of the barrier energy minus Fermi level divided by kT. So we can further simplify this expression, and we can realize that under exponent we have nothing but the difference between this level and this level. This is what we have under exponent, barrier height minus Fermi level at infinity. We can split it into the two parts. The first part is the barrier height, and the second part is the conduction band bottom at infinity and Fermi level at infinity. This difference would give us nothing but the carrier density at infinity, and the only exponent that we will have remained is the barrier height minus the built-in voltage minus applied voltage. It is a good home task to prove that the prefactor of this expression can be expressed exactly as the carrier density at infinity multiplied by thermal velocity divided by 4. It is a simple exercise. You just need to re-express once again the carrier density in a semiconductor. So I will write the final result here. It would be the thermal velocity divided by 4 multiplied by carrier density at infinity and multiplied by the combined exponent minus built-in voltage divided by kT and probably reduced by the applied voltage EV. This approach was, frankly speaking, we have found only this part of the current voltage characteristic. This is the part from which flows from semiconductor to metal. There should be one more computational part, the current flowing from metal to semiconductor, and it should be found by a similar way. It's just a sum over momentum moving to the right, velocity multiplied by distribution function in metal. We will not repeat these calculations because, first of all, the observation is that the current from metal to semiconductor is independent on the bias voltage, because when you bias the junction, the top of the potential barrier doesn't change. So the current from metal to semiconductor is voltage independent. So it is not a function of voltage, it is just a number. So we can find this voltage independent constant from the requirement that in equilibrium we should have zero flux. So we have found the flux from semiconductor to metal as a function of V. This is an exponential function. And the current from metal to semiconductor should be equal to the reverse current at V equal to 0. So we just find JMS as JSM evaluated at V equal to 0. This is very simple. The result is that you need to subtract unity from the expression for the Boltzmann exponent for EV. And let's look at some computational results. The computational results for evaluation of using the evaluation from Drift-diffusive and thermal injection model are shown in the graph here. So both functions are looking identical. They are exponential functions of the applied voltage. But there are some differences. The differences are the prefactors. The ballistic model tells that the current should be proportional to thermal velocity, and it doesn't know anything about the scattering parameters and in particular about distribution of voltage along the device. And this approach doesn't know anything about scattering. And there is another approach, and when we look at the drift diffusion approach, you will see that the current is proportional to the mobility and knows about particular distribution of potential landscape over the semiconductor junction. Definitely when you substitute the parameters, for example, for silicon, typical mobilities, typical doping densities, you will obtain two different results for drift diffusive and thermal injection models. I hope you will be able to answer which of the models is correct in which situations. So in which situations should we use the drift diffusive model, and in which situations we should use the ballistic model? There are two different answers to this question. The formal answer is that when the device length is much larger than length of free path, then we use diffusive model. And otherwise, when free path is larger than the length of the device, we use ballistic model. But there is one more practical answer to this question. The essence of this practical answer is that when we use a drift diffusive model, we think that the scattering in the bulk is the main limiting factor that hinders the passage of current. And when we calculate the current according to the thermal injection model, we think that the barrier height and its finite probably transparency is the limiting factor to the carrier transport. And you probably know the rule for summation of two resistances. If we have the resistance R1 and R2, or probably the conductivities G1 and G2, then the net resistance is always larger than each of them. And if we have more generally some structure with a narrow section and with wide section, then its conductance is defined by the narrow. Why am I telling about that? I'm telling this that the minimum of the two currents would be in most situations will give the correct result. So if the thermal injection model gives result being smaller than the result given by the drift diffusive model, as you see in this picture, then it means that drift diffusive model overestimates the transport, and the transport is indeed limited by the number of carriers that can jump over the barrier. Then the full current would be definitely that given by the poorest of the models. So the toughest section for the conduction would determine the conduction of the structure on the whole. So we can think that our Schottky device is a sequential combination of bulk that is limited by diffusion, so diffusive bulk, and some ballistic boundary. These models can be actually not competing to each other, and probably you can forget about these limitations if you consider them as sequential stages for electrons passage. First, the electron should pass through the diffusive bulk limited by mobility and carrier scattering, and then it should pass through the ballistic boundary. There are several examples in the other areas of physics that can hint on the combined model for the carrier transport in the Schottky junction. I will recall an example from molecular physics which you probably know and you have probably solved it. This is the problem about evaporation of liquids from the diffusion equation approach. The problem that can hint us about on the proper model for combined transport is the evaporation of water from a glass that is partly filled. So probably you have solved this problem in the molecular physics course. The glass has height h. The level of water is delta H, much smaller than H, and the diffusivity of water vapor is known and it equals to D. You need to find the evaporation rate, which is the number of evaporated particles per unit time. The number of evaporated particles per unit time can be found just as diffusivity multiplied by the derivative of concentration of water molecules with respect to the coordinate. And to evaluate this, you can just assume that the vapor at the water surface is saturated, so the density is equal to the density of saturated vapor, and the at the top surface, and the density is equal to 0 at the upper end of the glass. So you can estimate it as diffusivity multiplied by density of saturated vapor divided by height of the glass. But there is some paradox with these kind of solutions. It is associated with the fact that when the height is tending to 0, we will have the evaporation rate that tends to infinity. And this is very strange. For example, you can put your water not into the glass but into a plate so that it is just has a flat surface, and you can actually put this water droplet into the vacuum, and then the density of vapor will be approximately 0 here, and it would be the saturated density here, and you will get the evaporation rate tending to infinity. So this is quite paradoxical, and actually we would like to know what limits the evaporation rate in this situation. Is there any physical limit? Does anybody, can anybody guess what will limit the evaporation in this situation? Okay, this can be quite a complex stuff, and surface energy is a good guess. Actually, the result is related to the surface energy, like when you evaporate a droplet, there is some amount of molecules that are attempting to get outside. And this number of attempting molecules can be estimated from the conditions of detailed equilibrium. In detailed equilibrium, the number of molecules that are trying to escape the droplet is equal to the number of molecules that try to get inside. But this number of attempts per unit time is nothing but the number of returns in detailed equilibrium. But the number of returns is the density of saturated vapor multiplied by its thermal velocity divided by 4. So the number of molecules that run out of the glass in unit time cannot be larger than the number of molecules that are attempting to go out, which is the density of saturated vapor divided by thermal velocity divided by 4. So here you actually see the competition between two physical processes. The slow diffusion in the upper section of the glass and the ballistic motion of molecules that attempt to escape from the water to the saturated vapor. So here in the long section of the glass you have the diffusion process, and here in the lower section of the glass we have ballistic attempts to evaporate. And if the diffusion model predicts unrealistically large evaporation rates, then we need to go to conclusion that the number of attempts per unit time cannot be larger than the saturated vapor density multiplied by thermal velocity divided by 4. And how can we formulate it in more detail? We can solve the diffusion equation not with the boundary condition of saturated vapor at the upper surface, but we assume that the level of saturation is slightly below 100% here. When the saturation rate is slightly below 100%, then it means that the current at the surface can be presented from one hand as diffusion current in the top section, but on the other hand it can be presented using the ballistic formulas: density of saturated vapor minus the density in the beginning of the ballistic section. I denote it as C0 multiplied by thermal velocity divided by 4. So instead of solving the diffusion equation with constant boundary condition, I solve it here with the mixed boundary condition that equates the diffusive flux to the ballistic flux. The same thing can be done for the Schottky junctions. The same thing can be done, and we can actually assume that there is a section of semiconductor that is described by drift-diffusive equations. Drift-diffusive equations. And there is a short section which has length order of free path that is governed by ballistic equations. In this model, we don't assume that the Fermi level drops exactly to 0 at the surface, but it drops to some finite value of surface Fermi level, EVS. This value of EVS appears to modify both the expressions for the drift-diffusive current and for the ballistic current. The modification is quite apparent, and in the expression for the drift-diffusive current you integrate not from 0 to EV, but from surface potential to EV. And in the expression for the ballistic current, you say that the Fermi level of your particles is equal not to EV, but has slightly reduced compared to its bulk value. From this equation, you can find the surface potential EVS and substitute it into the current voltage characteristic. The physics here is similar to the sequential connection of two diodes, one of which is described by diffusive model and the other one is described by ballistic model. And the total voltage between them is equal to V. Finding the quantity Vs, the unknown Fermi level at the surface, is identical to finding the voltage drop in the middle of these two diodes. So the problem here is fully identical to sequential connections of drift-diffusive diode with IV curve IDD depending on V, and ballistic diode with its known ballistic IV curve I ballistic depending on V. So the result is that the current in diode structures can be limited both by diffusion in the bulk or by transmission through the boundaries. I think it was one of our last lectures because the December is already starting and we'll soon have tests. Probably in the next lecture I will speak about high-frequency transport in semiconductors and its applications in high-frequency electronic devices. So we will release the assumption of stationarity in the kinetic equation and we consider some deeply non-equilibrium phenomena. If you have any questions, please don't be shy to ask it now.